Welcome everyone. In this video, I will be covering section 15.1, is multiple integrals. But in this section, we are going to be covering double integrals over rectangles. Chapter 15 is all about multiple integrals. Suppose f is continuous function defined on a rectangle or given by AB cross CD, which means on the x-axis it is from A to B, on the y-axis it is from C to D. Write an expression for a double Riemann sum of f. If f of xy is more than or equal to 0, what does the sum represent? A double Riemann sum of f is sigma I varying from 1 to m and sigma j varying from 1 to n, f of xij star, comma yij star delta A, where delta A is the area of each subrectangle and xij star yij star is a sample point in each subrectangle. If f of xy is more than or equal to 0, then this sum represents an approximation to the volume of the solid that lies above the rectangle R and below the graph of F. So what it means is here it is only an extension of um, the single variable definite integral that you did in Calc 1 class. So this means this is the area under the graph of the function, area under f of x, bounded by x equal to a and x equal to b, bounded by the lines x equal to a and x equal to b. So if you have a graph which is f of x like this, and if it is defined between the lines x equal to a and x equal to b, vertical lines, then what this integral represents is the area. To represent this area, we divide this into number of subintervals, and then we consider rectangles, either with the help of left hand points or the right hand points and so on. So if I add areas of all the rectangles, so it is going to be width times a height. If I consider a rectangle here, it's going to be width times height. Width of this rectangle is going to be delta x. Height is going to be a sample point, height at that point. So f at xi star, where xi star is a sample point in that interval. So what we are doing is we are finding the area delta x times height, and then we make a Riemann sum out of it. Then limit is n approaching infinity, sigma I varying from 1 to n. We do this for every rectangle, f of xi star delta x. So these are all areas of the rectangles. Again, similar idea, because it is double integral. F of xy is what our surface is, which is a function of two variables. So the surface is shown in blue. So what we do is we divide the x-axis, we have shown here, and then we consider a rectangle over which the surface is defined. The rectangle is as shown in the second figure R, and then we divide the x-axis from A to B. We divide from A to B into m subintervals. Then we divide the y, which is c to d, into n subintervals. So you get smaller rectangles like this. R is divided into number of subrectangles. And then you're going to find out the volume above each of these subrectangles. So it is height of the surface above that subrectangle times area of the base, which is area of that rectangle. So that's going to be, so if I consider one sample volume over the rectangle Rij, so I get f of xi star yj star, which is a height um, above that rectangle, and this is the area. So area times height will give you the volume. So we consider the volume of each of these, what's shown here in this diagram is the volume above the rectangle Rij. So we do this for all the rectangles that we have divided R into. So we get lots of volumes and we are going to add them all to give the Riemann sum. And that is going to be approximated and written as a double integral. Riemann sum, infinite Riemann sum, can be written as a definite integral. So we do this for double integrals. So we are going to have a double integral notation. So that is the idea behind this double integral being a volume. But here the surface is defined over a rectangle. In the next section, we are going to see surface defined over any kind of region, not necessarily a rectangle. Write the definition of double integral over R, f of xy dA as a limit. Double integral over R, f of xy dA would be equal to limit as m and n approaching infinity, sigma I varying from 1 through m, sigma j varying from 1 through n, then height of the surface at the Rij rectangle. So f of xi star, f of xij star, yij star, which is xij star, yij star is a sample point in the rectangle Rij, in the subrectangle Rij. So this is the height times the area of the subrectangle, which is delta A. So what is the geometric interpretation of double integral over R, f of xy dA, if f of xy is more than or equal to 0? What if f takes both positive and negative values? If f of xy is more than or equal to 0, then double integral over R f of xy dA represents the volume of the solid that lies above the rectangle R and below the surface z equal to f of xy. In case f takes both positive and negative values, then double integral over R f of xy dA is v1 minus v2, v1 minus v2, where v1 is the volume above R and below the surface z equal to f of xy, and v2 is the volume below R and above the surface now v1 minus v2 is called the net volume. The idea here is just similar to the idea that we had in calculus 1. If a part of the area is above and part of it is below, let's say, then if you do the if you do the integral from point A to point B, then integral A to B fx dx would be area above the x-axis, which is positive, minus area below the x-axis, which is minus A2, which is said to be the net area. This is calculus 1. Similar idea, because we are talking about a surface, if part of the surface is above, um, if the part of the surface is positive and part of the surface is below, above the z-axis and above the xy plane, and part of it is below the xy plane, then we consider V1 to be the volume above R and below the surface, V2 to be the volume below R and above the surface. Here, R stands for the rectangle. So we consider the surface above the rectangle and below the rectangle. So in the earlier case was all above the rectangle. So it is just the volume of the solid that lies above the rectangle or and below the surface. In case a part of the surface is above the rectangle and part of it is below, then it becomes the net volume. How do you evaluate double integral over R f of xy dA? We usually evaluate double integral over R f of xy dA as an iterated integral by using Fubini's theorem, which says double integral over R f of xy dA equal to double integral um, f of xy dy dx. So if you consider inner integral with respect to y, then you have to consider the limits for y inside. Then outside it is x, outside it is x. So x equal to a to b. You have to write down the limits for x. So that will be outer one. It can also be written as, can write down this integral, same integral as integral c to d, then integral a to b f of xy. Now you are writing inner integral is with respect to x, so that will be x. And the outer integral is with respect to y, so that will be dy. So you can, in a rectangle, when the surface is defined over a rectangle, the problem is kind of simpler. So you can actually switch x and y, and with respect to y first and then with respect to x after, or with respect to x first and with respect to y after. Either way you can do, but only thing is you have to be careful with the limits. What does the midpoint rule for double integrals say? It's again similar to the idea of calculus 1 midpoint rule evaluation of an integral. The midpoint rule for double integral says that we approximate the double integral over R f of xy dA by the double Riemann sum, which can be written as limit m and n approaching infinity, double sum, one for the subintervals of the x-axis, the other one for the subintervals of the y-axis, or the subintervals between a and b represents I to m. The subintervals from C to D represent from J to J varying from 1 to n. Then f of the midpoint xi bar yj bar That's a midpoint of the Rij interval, a rectangle, times delta A, where xi bar, yj bar are the centers of the subrectangles. Instead of the word midpoint, we will use center because it is the center of a rectangle, subrectangle. And in the section videos, videos for this section 15.1, I have done the following problems. Problem number 1, problem number 29, problem number 39, problem number 42, and problem number 24. Please refer to the section videos for these problems. Refer to section videos. Refer to the videos for section 15.1. So as a sample, we will do one problem here in this video. We will try from the additional suggested problem. Let me show you how we can do problem number 19. We will try problem number 19. Calculate the iterated integral, integral negative 3 to 3, integral 0 to pi by 2, double integral, y plus y square cosine x dx dy. So the way you look at the problem is that which one you need to integrate first. Always the inner integral first. So you have to do the integration from 0 to pi by 2 y plus y square cosine x. Then with respect to dx first. With respect to dx first. And then you're going to integrate with respect to y. So we have to consider this integral because it is an inner integral. Inner integral is with respect to x. So the inner limits are 0 to pi by 2. The outer integral is with respect to y. So the outer limits are, bounds are from negative 3 to 3. So first you have to go inner integral first. The inner integral first is what you have to do. So let's keep the outer integral as is from negative 3 to 3 with respect to y. We'll keep this one as is. Then we are going to integrate y plus y squared cosine x with respect to x. When you integrate with respect to x, you know that y needs to be treated as a constant. Just the way you did partial derivative. You have to keep y as a constant. Y is a constant. Imagine you give a number to y. So imagine that y is equal to k. Then you are integrating k with respect to x. So it is yx plus y square, which is a constant, then integral of cosine x, which is sine x. Now you're going to plug in the limits 0 through pi by 2 for x. Then you're keeping, after you evaluate this, then you're going to evaluate this with respect to, integrate with respect to y. That is the last part. Okay, now y from negative 3 to 3, we will keep it as is. Now you're going to plug in the limits for x here. So it is pi by 2 for x times y plus y square sine of pi by 2, which is equal to 1. Then you're going to plug in x equal to 0 at the lower limit. So because of the presence of x here and sine x, the lower limit is going to be 0. So it is only integral with respect to y now. So in the next step, we are going to integrate with respect to y, which is a outer integral now. So now integrate with respect to y. So it is negative, integrate with respect to y. So pi by 2 is a constant. Then y square over 2, integral of y. then y cube over 3 between the limits negative 3 and positive 3. So it is pi by 4 y square at the upper limit, so that will be a 9. Then upper limit y cube over 3, so it will be uh, 27 over 3, which is equal to 9. Then minus, at the lower limit, you are going to plug in negative 3 for y. So it is pi by 4 times negative 3 square, which is positive 9. Then at the lower limit, it's going to be plus negative 3 cube, which is equal to negative 27 over 3. That will be negative 9. So it is going to be 9 over 4 pi plus 9 minus 9 over 4 pi plus 9. So you're going to have this 9 over 4 pi is getting cancelled. So it is 9 plus 9, which is equal to 18. So as a conclusion, we can say double integral as given in the problem, negative 3 to 3, then 0 through pi by 2 of y plus y square cosine x dx dy equal to 18. Hope this video helps.